Section 1.3. Why deep learning? Why now? The two key ideas of deep learning for computer vision, convolution neural networks, and backpropagation were already well understood by 1990. The long short-term memory LSTM algorithm, which is fundamental to deep learning for time series, was developed in 1997 and has barely changed since. So why did deep learning only take off after 2012? What changed in those 2 decades? In general, three technical forces are driving advances in machine learning: hardware, datasets and benchmarks, algorithmic advances. Because the field is guided by experimental findings rather than by theory, algorithmic advances only become possible when appropriate data and hardware are available to try new ideas, or to scale up old ideas, as is often the case. Machine learning isn't mathematics or physics, where major advances can be done with a pen and a piece of paper. It's an engineering science. The real bottlenecks through the 1990s and 2000s were data and hardware. But here's what happened during that time. The internet took off, and high-performance graphics chips were developed for the needs of the gaming market. Section 1.3.1. Hardware. Between 1990 and 2010, off-the-shelf CPUs became faster by a factor of approximately 5,000. As a result, nowadays it's possible to run small deep learning models on your laptop, whereas this would have been intractable 25 years ago. But typical deep learning models used in computer vision or speech recognition require orders of magnitude more computational power than your laptop can deliver. Through the 2000s, companies like NVIDIA and AMD invested billions of dollars in developing fast, massively parallel chips, graphical processing units or GPUs, to power the graphics of increasingly photorealistic video games. Cheap, single-purpose supercomputers designed to render complex 3D scenes on your screen in real time. This investment came to benefit the scientific community when, in 2007, NVIDIA launched CUDA, found at this link, a programming interface for its line of GPUs. A small number of GPUs started replacing massive clusters of CPUs in various highly parallelizable applications, beginning with physics modeling. Deep neural networks, consisting mostly of small matrix multiplications, are also highly parallelizable, and around 2011, some researchers began to write CUDA implementations of neural nets. Dan Sirsan and Alexei Kirshevsky were among the first. Footnote 6. See Flexible, High-Performance Convolutional Neural Networks for Image Classifications, Proceedings of the 22nd International Joint Conference on Artificial Intelligence from 2011, found at this link. Footnote 7. See ImageNet Classification with Deep Convolutional Neural Networks, Advances in Neural Information Processing Systems 25 from 2012, found at this link. What happened is that the gaming market subsidized supercomputing for the next generation of artificial intelligence applications. Sometimes, big things began as games. Today, the NVIDIA Titan RTX, a GPU that cost $2,500 at the end of 2019, can deliver a peak of 16 teraflops in a single precision, 16 trillion float 32 operations per second. That's about 500 times more computational power than the world's fastest supercomputer from 1990, the Intel Touchstone Delta. On a Titan RTX, it takes only a few hours to train an ImageNet model of the sort that would have won the ILSVRC competition around 2012 or 2013. Meanwhile, large companies train deep learning models on clusters of hundreds of GPUs. What's more, the deep learning industry has been moving beyond GPUs and is investing in increasingly specialized, efficient chips for deep learning. In 2016, at its annual I/O conference, Google revealed its Tensor Processing Unit, or TPU, project, a new chip design developed from the ground up to run deep neural networks significantly faster and far more energy efficient than the top-of-the-line GPUs. Today, in 2020, the third iteration of the TPU card represents 420 teraflops of computing power. That's 10,000 times more than the Intel Touchstone Delta from 1990. These TPU cards are designed to be assembled into large-scale configurations called pods. One pod, 1,024 TPU cards, peaks at 100 petaflops. For scale, that's about 10% of the peak computing power of the current largest supercomputer, the IBM Summit at Oak Ridge National Lab, which consists of 27,000 NVIDIA GPUs and peaks at around 1.1 exaflops. Section 1.3.2 Data. AI is sometimes heralded as the new industrial revolution. If deep learning is the steam engine of this revolution, then data is its coal, the raw material that powers our intelligent machines, without which nothing would be possible. When it comes to data, in addition to the exponential progress in storage hardware over the past 20 years, following Moore's law, the game changer has been the rise of the Internet, making it feasible to collect and distribute very large data sets for machine learning. Today, large companies work with image data sets, video data sets, and natural language data sets that couldn't have been collected without the Internet. User-generated image tags on Flickr, for instance, have been a treasure trove of data for computer vision. So are YouTube videos. And Wikipedia is a key data set for natural language processing. If there's one data set that has been a catalyst for the rise of deep learning, it's the ImageNet dataset, consisting of 1.4 million images that have been hand-annotated with 1,000 image categories, one category per image. But what makes ImageNet special isn't just its large size, but also the yearly competition associated with it. Footnote 8. The ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, found at image-net.org/challenges/LSVRC. As Kaggle has been demonstrating since 2010, public competitions are an excellent way to motivate researchers and engineers to push the envelope. Having common benchmarks that researchers compete to beat has greatly helped the rise of deep learning by highlighting its success against classical machine learning approaches.